So, we have a sign convention worked out for electronic systems and for translational mechanical systems. And today we're going to round it off with rotational mechanical systems. This is still lecture 2.2. I decided to tack it on at the end of 2.2 instead of adding a separate lecture because I thought it fit under the heading of sign convention fairly well, considering it is part of the sign convention. This is very parallel to the translational mechanical system. So in a similar way, we're going to introduce the convention and then have this inline example going on the right, because I think that it kind of needs some illustration. And we'll get to the towel thing, but not yet. We're not there yet, so we'll get there. Okay. So the system we're going to demonstrate this on as we introduce the convention is a flywheel or some rotational moment of inertia with a torque source applied to it, and that is connected to an inline spring element that connects to ground. Okay? So that is our simple little system that we're going to use to illustrate the sign convention. So the first step, once again, is to assign a coordinate arrow. Assign the sign by drawing a coordinate arrow. So we do that here. The green arrow is our coordinate arrow. And we're always, when we draw an arrow like this for a rotational system, what we mean is a rotation in the direction that the right-hand rule would give if we aligned our thumb in the direction of the arrow, the direction of the arrow. So, right hand, don't use your left hand, use your right hand. In the direction of the coordinate arrow means that rotations in this direction are positive. Okay? So, that is our coordinate arrow. So now we're ready to go. We did it in the direction of the source, and that's our preference, right? So, if possible, we do that. It's just kind of like a nice thing to do. If you have multiple sources and one of them happens to be, or some of them happen to be in opposite directions, then you can't always do that. So that's why it's just preferred and not required, because we don't like to require impossible things before breakfast. So, you guys know that reference, right? Who said it? Oh, I think it's from a famous piece of literature. Something about attempting a certain number of impossible things before breakfast. I don't know. It's a whole thing. You guys should look it up. Look it up.
Wonderland?
Yeah. I think it is Alice in Wonderland. There's a lot of good references in Alice in Wonderland. On the sort of like, I want to say surrealist note, because I think Alice in Wonderland is kind of surrealist. Do you guys watch Futurama? Yeah. I really want there to be somebody out there who makes a Creative Commons open illustration of Hypnotoad. I love Hypnotoad, and I would love to include him in these lectures. Hypnotoad. There's this in the measurements class. The notes I'm preparing for today's lecture are really fun, and there's this one part where it's super meta. I want Hypnotoad just it would be awesome, but I couldn't find one. There's only ones that it would be technically illegal to rip off, so I'm not going to do it myself because I ain't got time for that. Okay, so let's draw a linear graph. First without arrows, and then we'll add the arrows on. We're almost getting to the point where we're comfortable. We know we're doing the homework. We're drawing linear graphs. We're getting a little bit more familiar with them. So we're almost to the point where we can start drawing the branch and the arrow at the same time. But we'll start still with just bare branches, as if it was just the very beginning of spring. Okay, so the first step is to identify the nodes. So the nodes that we have are, we have a rotational moment of inertia that has some distinct angular velocity, right? So that's going to have a node. There's also going to be a node associated with ground, always a node associated with ground. Are there any other nodes to be concerned with in this? No. No. Not that I can see. So we have our two nodes, moment of inertia node and our ground node. And we can start filling in the branches then. Clearly, the moment of inertia node is going to have a moment of inertia branch, and it always goes to ground, right? So draw that guy in there. The source, torque sources, always originate at ground, essentially always originate at ground, and always insert or are connected to the node of application. So it is applied to this moment of inertia, therefore it has to connect to the moment of inertia node right here. So that one is pretty straightforward, the torque source. And then finally, the spring connects from the moment of inertia node directly to ground, right? It connects between these two nodes, so it also connects like that. Okay, so any questions on just the bare linear graph? I know we're still getting used to drawing them, so it's fine if there are any questions. It's always fine if there are questions. It's just more fine right now. Okay. Okay, let's start assigning some arrows then. So, spring and damper directions. So on each inline spring and damper element, define the positive velocity drop and therefore the branch arrow to be in the direction of the coordinate arrow. Okay, so this is an inline spring. It happens in line with the shaft. If there was another element over here, this would connect to that shaft element. So in the direction of the coordinate arrow is from left to right. Okay? And we encounter first this moment of inertia node, and then we encounter the ground node going left to right. Therefore, we have to draw our arrow going from the moment of inertia node to ground. Okay. Furthermore, springs and dampers that aren't in line typically connect to ground. So the quintessential example of a damper that is not an inline damper is the bearing element. So if we have a bearing, almost always the inside of the bearing connects to the shaft, right? And the outside of the bearing connects to the chassis, whatever that is. So some sort of housing. And that's typically going to be fixed, or that's going to be a reference velocity typically. So that's what we mean when we say that they typically connect directly to ground, is they go from the shaft velocity as one side, one velocity side, to the chassis on the other side. So when we have those springs and dampers that are not inline, we connect them, they're almost always connected to ground. We always orient those branches toward ground. There are some really weird edge cases that you almost have to construct. And in those cases, we'll just assign the arrows any way we feel because the convention doesn't apply to them. So that's fine. Just to be a little cautious in interpretation then. When you do the interpretation, you have to be a little careful. But we probably won't encounter any of those in this course, and they're not that common. Okay, assign inertia direction. So on each inertia element, define the positive angular velocity drop and branch arrow to be toward ground. This is the same as the mass one, right? They're easy. Whenever you have a moment of inertia or a mass element, you draw to ground. They always connect to ground, and you always draw the arrow to ground. The spring is still pointed to ground. Sometimes we dash this J branch, the latter half of it, to remind ourselves that it's sort of virtually connected to ground, right? Because the moment of inertia is not like fixed to ground. It's just that it's referencing ground always because it's a good old-fashioned Newtonian inertial element that always has to have an inertial reference frame. All right. Then we assign torque source directions. So we still have our spring and our inertial directions, and then we can use this convention for the torque source. On each torque source element, define the positive direction as follows. So in the ideal case, which is that the torque source has the same definition of positive as the coordinate arrow, which is our case, right? We have our torque source to the right, and we have our coordinate arrow to the right. So that's what we've got. Then we use the following interpretation, the following convention. We draw the coordinate arrow toward the node of application. The node of application of this torque source is this J node, right? The inertia node. So we draw the arrow toward that node. If we had jackassedly drawn our coordinate arrow to the left, it can be an adverb, right? Then we would have to draw the arrow pointed the other direction, away from the node of application. Okay. So this would instead point this direction. But this is not our coordinate arrow because we did not jackassedly do that. All right. Somebody once told me that the English language is meant to be manipulated and like new words created by mashing things up. And that just gave me a lot of freedom, and I really like that. I have held on to that. He's an English professor, so like I feel like he knows. I don't know. All right. So assign angular velocity source directions. On each angular velocity source element, define the positive direction as follows. So in the ideal case, when you've got your source arrow and your coordinate arrow pointing in the same direction, then draw the arrow for your angular velocity source away from the node of application. Okay, and that is not what we have in our situation here. We don't have an angular velocity source. We have a torque source. Well, let's just pretend. If you can imagine for a moment, we have an angular velocity source with a heavy pen here, omega s. And if that was the case, then this is all imaginary, right? It means it has, complex plane representation. That was just a stupid joke. Okay, it doesn't. So we have the coordinate arrow and the imaginary angular velocity source both pointed to the right. Therefore, we are going to follow this ideal case here, draw the arrow away from the node of application, which is that direction. And we're done. That's our whole convention. All the convention, all the time, in one place. Now we have the cool table of interpretation. I feel like I need to have like something. Like a hat I should put on. I'm not sure what. Something should be happening when I say that, because table of interpretation is too cool of a term. Okay. Get out your towels, but don't use them yet. Okay. It's important you not use them yet. If you use it, you lose it. So, I don't know. That was actually the opposite, I think, is what I paid attention in health class. So, on the left-hand side of the table, you have torque interpretations. On the right-hand side of the table, you have angular velocity interpretations. So, we're interpreting signs, right? So, if we have a positive torque or a negative torque, we're either in positive torque column or negative torque column, positive angular velocity column, negative angular velocity column. Okay? And each row corresponds to a different element. So, if we have a positive torque on a moment of inertia element, J, then we interpret that to mean that the torque is in the direction of the coordinate arrow, which is to say if we have our right thumb pointed in the direction of the coordinate arrow, the torque is being applied in that direction. If we have negative torque on a moment of inertia element, it means the torque is in the opposite direction of the coordinate arrow. So if our coordinate arrow is pointed this way, then this is the actual direction. Okay? Angular velocity on a moment of inertia, if it comes out positive, it means the velocity is in the direction of the coordinate arrow. So, and if it's negative, then the velocity is in the opposite direction of the coordinate arrow, like that. So I really probably should. It's hard to do that. Like that. Okay. Now we get to use our towels. This is actually my wife's scarf, but it has stripes that go longitudinally, so I think it's easier to see. Also, my ShamWow was dirty, so I couldn't bring it, because that was weird. I don't want to bring a dirty towel. So, I actually think this is better if you partner up. So if you have a towel, try to partner with somebody who was unprepared. Let's just say that they were underprepared. Maybe they were prepared to some extent, underprepared. And if you don't have a towel, get with somebody who is, maybe not superior in all ways, but at least in this way, has a towel. And partner up, and I don't see you moving, and one of you grab one end. Each of you grab one end with your right hand. Okay? So you grab it with your right hand. And we're going to use the right hand rule here. So this is it's important you grab it with your right hand. Also grab it so that your right thumb is pointed at your partner. Okay? All right. Now we're going to consider ourselves to be each of us oriented on a branch, a spring or a damper branch, and we're here at the tail end of this branch. Okay? and our thumb is pointed in this direction of the arrow. Each of us can think of ourselves as being like that. Okay? Now, if you have a torque that comes out positive on a spring element, then that is like if you ring in the usual sense of wringing this towel. So try to, you have to kind of twist it a few times before you really get a good feel for it. But if you wring it in the direction, so follow your fingers around in the positive right-hand rule sense and twist that direction. That is your positive torque. Notice this sort of twisting that's happening, and you can see the lines that emerge in the twist, right? Those lines correspond, if you're looking down at your towel, correspond to these lines here in the diagram. Okay? So you guys can always remember this moment you shared with your partners of twisting this and seeing those lines and corresponding to this table of interpretation. Okay, like this. All right, now you can kind of like let the slack out and then start twisting it the opposite way. So like you're revving the engine of a motorcycle, which you should never do because that is annoying as hell. So I have a thing against that. You have, it's twisted this way. You are like you're revving a motorcycle, and you're like, and this is, remember, it's wrong. It's wrong to rev a motorcycle. We don't like that. I have a thing against, I've lived in an apartment across the street from a biker bar and a strip club. So at 2 a.m., at 2 a.m., the bikers all wanted to seem really cool, I think, for the strippers. I'm not really sure, but all I know is I was laying in bed and I lost my cool more than once. I didn't go confront them because bikers are big, but yeah, I was secretly angry. But I was in Seattle, so we don't really actually confront. Yeah. So wrong is this other way of twisting. Okay, and that is interpretation for both the spring and the damper element, the sort of the twist that you're undergoing. Okay? All right. That was the towel thing. You guys can let go of your towels now. It's cool. Oh, ouch. Yeah. I asked my wife this morning as I was leaving the house, I said, could you have do you know where the ShamWow is? She's like, I think it's dirty. And I was like, man. And I saw her scarf, and I was like, can I take your scarf? She was like, what are you going to do with it? No. And I was like, don't worry. There's very little wiping off of things that will be done. Just mostly, just a little demo. No big deal. Okay, so we also have for the spring and the damper the interpretation of the sign of the velocity, angular velocity. So the angular velocity that is positive means that it drops in the direction of the coordinate arrow, meaning that if you're thinking about this, you're twisting faster on one end than you are on the other end, in the direction of your coordinate arrow. So in the positive sense, that means that your tail of your branch is moving faster than the head of your branch. Okay, so tail, head. The tail is moving faster than the head, meaning that the velocity is higher at the tail than it is at the head. And then if you have a negative value for velocity drop across a spring or a damper, that means that your angular velocity at the tail is slower than the angular velocity at the head. Okay? So you have a velocity gain across the element. And that is the entire table of interpretation. And that leaves us with a fun example. It's all that remains. So, for the system shown, draw a linear graph and assign signs according to the sign convention. Dun, dun, dun. So, I am going to do the first step with you so we're all on the same first step page, and then we're going to break off, work on this problem a little bit, and then we'll come back together. So, the first step is always to do what?
Draw ground.
Well, so before we even draw ground, it's good to draw a coordinate arrow. Yeah, draw a coordinate arrow because then we have a definition of what is going to be positive for any of our elements. So there's our coordinate arrow. Let's draw to the right. Why did I choose to the right? Torque source is to the right. Also right is better. No, just because the torque source is to the right. If we can, we prefer to have them in the same direction. Okay? All right, so now I want you guys to try to work on the construction of the linear graph on your own, and I will walk around and give guidance as is requested of me. I left you guys plenty of room, so do your own version, like above, and then we'll come together and you'll have plenty of space to draw another one that we do together. So before we go too much further, I just want to get on the same page on one aspect at least. How many nodes are there? Two nodes in addition to the ground, right? So there's the ground node always, and then there are two distinct angular velocities, one for each of these A-type energy storage elements, the rotational moments of inertia. So 3 total nodes, one of them being ground. All right, let's try to come together and talk through it. I want to draw this one not oriented horizontally like the others. I want to actually put our ground at the bottom. And I always start with the ground node when I draw these. I follow that by the other nodes. So draw all the nodes first and then connect them with the branches. So we said that there are 3 total. There's the ground, and there's a J1 node and a J2 node, right? So I'm going to draw the J1 here. I'll draw the J2 there. And it's kind of easiest to start oftentimes with those inertia branches because they always connect from their special node to ground, right? They always do because we have to reference ground for the dynamics to work out. So we don't have to dash, but we can dash the moment of inertia. And let's start. Let's see if we can take a step and start drawing our arrows as we construct it. J1 is going to go towards ground because every inertia element is oriented towards ground, right? That's our convention. And J2 is going to be the same. I chose to dash the lines, not required, but it's just to remind us that these are virtual connections to ground and not actual physical contact connections. So that is our start. I then usually like to draw the sources in. So although you can kind of do it in any order, if I don't do them in a certain order, I forget. I forget elements, and then that's a problem. So, okay. Torque source is applied to J1, right? So it's got to be connected to J1, and we said torque sources will connect to ground. So there's our torque source. And we have to draw an arrow on it. And so this one requires a little bit of sign convention interpretation, right? We have our coordinate arrow in the direction of the torque source. So for the torque source, that means that the arrow is oriented, is it away or toward the node of application? Toward. That's right. It's toward. Great. Now, I think this, so we'll do the dampers next, and then we'll do the spring last. So with the dampers, we have 2 different types. We have this bearing type, and then we have this drag cup type. The bearing type is not inline. The drag cup type is an inline element. Notice because it connects to 2 sides of the 2 shafts there. So with this side of it and the other side of it. And this bearing, B1, it goes from this angular velocity of the shaft, which we assume, this diagram doesn't say anything to the contrary, is the same angular velocity as the moment of inertia, J1. So it starts here, at this J1 node, and the other side of this bearing is connected to the chassis, which we say is grounded. Right? It's our reference angular velocity. So that leaves us with the other side being ground, and our I don't want to draw the arrow. I want you guys to help me with that. So I got to draw the arrow, and this is not an inline damper. This is the other type of damper. And so we said in the convention that whenever we encounter these, we draw them to ground, right? Okay. B3, it's going to be the same, right? It's just another of these, but it's connected to the J2 node. our B3. And what about our B2? Which two nodes does it connect?
1, 2. J1, J2.
Yeah, J1 node to J2 node. So it goes like this. And what direction should we draw the arrow?
Left to right.
Left to right, because J1 is, so our coordinate arrows goes left to right. So J1 is encountered first going left to right before J2. So it has to go from the J1 node to the J2 node, which is left to right. Okay, so we should label that B1, or sorry, B2. Okay, so we have our last branch for our graph, and that is the spring, K. Which two nodes does it connect?
B3 or J2 and ground.
Yeah, J2 and ground, right? So K. Now, oh, I drew the arrow towards ground. This is an inline spring. You can have, so it's a little ambiguous in this case because it is connected to ground, but it looks just like an inline spring the way that it's oriented here. We would probably draw a spring that's not inline and in a different way. So we interpret this as an inline spring. So we would go from left to right, the direction of our coordinate arrow, J2 to ground, so J2 node to ground. So there is our linear graph with all of its arrows drawn in. So we can construct a linear graph. Not too bad. So I want to talk for a moment about this system that we're looking at here, like what this might model. Okay. So the torque source comes in here. Maybe this is like a motor of some sort, and this side here is the drive side with the motor connected to it. And this side over here is going to be like the load side, right? And then there's a coupler. So this could represent a lot of different systems, but oh man, there's a snowball fight going on out there. I mean, like, those people were pelting each other. Oh, there we go, another one. It's like the wettest, slushiest snow. I bet that's like ice balls, just wham. Yeah. Okay, so maybe we should wrap up early and go join them. But I want to at least discuss one possibility. So this is kind of an interesting. I'm teaching in the measurements class. Some of you are in that class as well. And you could think of this as being one way to measure something. Let's see what it would measure. So you could have the drive. So say you spin up the drive side. So you apply some torque from the torque source. It spins up to some angular velocity. This drag cup that couples these, it transmits torque in proportion to the angular velocity difference across it, right? So let's say that J2 started off with no angular velocity, and we started to spin up this side over here. Well, this other side is going to respond, right? There's going to be torque transmitted. And it's going to respond. If we looked at it from the side, we would see if we like stuck a needle on it, then this would start to turn, but it's being resisted. There's a spring to ground here, right? It's kind of an unusual situation in a rotational system of a spring to ground. But if you have a spring to ground, it's going to resist the motion, right? And at some point, the torque, so if you speed this thing up, as the speeds are far different from each other, the equilibrium torque is going to be, at some angle, right? But, so you could indicate the sort of the difference in speed there. Then, once this thing had J2, but J2 is never going to totally catch up to J1 though, right? Because this spring is going to resist it from turning. So if you keep turning J1, J2 is going to try to keep turning, but that spring is going to resist it more and more and more, right? So it's going to kind of stop. And you're going to have J2 pretty much stationary, where J1 just going along. And that equilibrium angle that it's at is going to be proportional to the speed difference between these two. So in equilibrium, this actually could be a speedometer, right? This would be, you would have to calibrate it, but in equilibrium you could say, oh, well, this is like 1,000 RPM or something. So it's an indicator of the speed, so this would be 0, maybe this is 1,000. The speed of this is in equilibrium going to be indicated on the angular position of J2. So that's the type of thing you could do, or the type of system you might want to model in a dynamic systems way like this. And questions you would ask would be like, okay, how long when I have a change in my drive speed, like a sudden change in my drive speed, how long does it take to get to an equilibrium with the indicator? How long does it take for that indicator? Because that needle is going to move and it's going to probably bounce around a little bit because there's a spring, right? So it's going to respond and it'll probably damp out. But how long does that take? Is it something that takes a long time? Can I redesign the spring here so that maybe it responds in a way that I prefer? So you might also ask questions like maybe you could try to calibrate it in a theoretical way, like a certain speed would be associated with a certain angle of rotation of J2. And there are lots of different things you could do with it, but that's the sort of thing you can start doing once you think of a measurement system as a dynamic system. And it always has to interact with the system it's trying to measure in a dynamic way, right? So these sorts of, in a sense, it seems like a toy problem, right? We're like, when do we ever see a flywheel connected to another flywheel with a spring connected to ground? Well, you don't see like that. People don't build a system that looks like that. But it could be used to model something that would be a real measurement system. And one more note on like the sort of realness of this. The B1 and B3 bearings, you might look at them and say, well, that's a pretty bad design because you don't really want to have a bearing only on one side when you have a moment of inertia cantilevered off, because the bearing has to then support the moment of this, the weight of this. And so you're going to get some flex, that's exaggerated, but it's going to flex some from the weight of J1. And so the moment you have to have the bearing take is not good for the bearing, first of all. But also you can get wobble too. So if there's a lot of deflection, the J1, when we start spinning it up, it starts to, it's oriented like this, and then it tries to like flip itself over and then flip itself back. So it starts to wobble, and it's really loud. And it can cause all kinds of vibration issues, and people don't like when their systems are making lots of noise. So it's generally just not a good idea to have wobble in your systems. So we typically would put a bearing on both sides, okay? Bearing on both sides of any rotational inertia. However, if it's a very short cantilever off and it's a relatively light load, you might be able to get away with a bearing on just one side. And if you have so the other issue, the other question is, if you have bearing on both sides, would you need to have two of these lumped parameter bearing elements? So what do we have to have? A B1, a B2, a B3, and a B4. And the answer is no, because I mean you could just stick another like another B1 off here, so they're the same. So it'd be like another B1 right there. But you could then just combine the damping effect from the two and make it one lumped parameter element. So that's what we would typically do. If we draw one bearing, it's not to say that's the design, put one bearing on this. What we're saying is, even if there are two bearings, which there probably are, we can treat them as one bearing and just have a lumped bearing damping.
Kind of like combining resistors in a circuit.
Exactly like combining resistors in a circuit. Yeah. So we often, when we model these, we'll put in just one, but in reality, in our design, we'll probably put in two. But we'll have to, in determining what B1 is, we have to take that into account, right? There's one bearing versus there's two bearings, has an effect on the value of B1. Just like if there were two resistors versus one resistor, it'd have an effect on the value of that resistance. But it has the same effect on the system. So we can just treat it as a single one. It simplifies the linear graph. It simplifies our analysis to do it that way. Although we don't have any loss of generality in terms of the dynamics. It's the same. Okay? All right. So that's it. Quiz today. I'm going to make it due tomorrow, though, because I realized that like today's material is kind of covered in the homework, so I'm going to give you guys a little leeway. But I'll still put it up today. And yeah, have a good weekend.